We finish. There's a lot of topics. And actually, this is like multivariate analysis in ecology is kind of like a semester course. So I will just go super fast. And the intention is to just like make a span of what happens when you analyze this kind of data, but also to introduce a little bit to cluster and ordination. We have been talking about this kind of data that of analysis where the response matrix is not a variable, it's not a vector, but it's a whole matrix, like a community matrix, a species per sites matrix. Other kinds of data in other areas function the same. You can have patients and variables, you can have bacteria and genes. It's not unique to the topic. And we can have predictors and variables that can be species in this case, but also environmental variables, like soil conditions, environmental conditions, and pH and temperature. And I have been talking during this week about pairwise comparisons between the objects and between the variables. So for example, we used Gower distance to compare species based on their traits. And there's a lot of distance theory about how do you actually effectively measure distances between objects. And one of the problems is that Euclidean distance, like the difference of x's and the difference of y's, and it's Pythagoras, does not work in this kind of data because we have abundances. So if you remember the two communities, the fake communities that we did yesterday, a couple of days ago, we had a community that was not even at all, and we had a community that was more even. And imagine that they share some species, but they do not share some other species. So one of the questions is, what does it mean to be similar in terms of community? If you have 5 species and 2 communities share species 1 and 2, for example, and another species has only species 4 and 5, and you calculate Euclidean distance. If, for example, these species have low abundances, even if they're shared, the fact that the numbers are high will make Euclidean distances explode, and you won't have good Euclidean distance measurements between compositions that share the same species. So lots of distances are not geometrically thought, but in terms of sharing species and sharing absences. I will come back to this. So between objects, that means between sites, most of the distances that have been worked are in terms of shared presences or absences. And it's basically a confusion matrix where you can have species that are in both sites, species that are in one site but lacking in the other, and species that are missing both sites. Some some dissimilarity metrics give lots of importance to the sharing of species. If you have the same species, this is going to be more important. So A will have more weight in the dissimilarity metrics than D, for example. And others are balanced between the shared presences and the shared absences. And in biology, at least in this kind of sampling, that makes sense because when you, that's a long discussion, because when you find the species in a place, that's a real absence, that's a real presence. You know the species is there. But when you do not find the species in a place, you don't know if it's a real absence. You cannot trust the data of absence. You have no evidence of the absence. So it's more important to have evidence of the shared presence and to think a lot about what does it mean when you don't have a species in a site. So D should be less important, less informative than A when you build this kind of indexes. In vegan, in the package vegan, it's a long help, and you can start reading a little bit about it. It has lots of options, and not all of them are there to be used, but also for historical purposes, because this has been changing in time. So VegDist is the function for dissimilarities in this area, but also you can use dist, like functions dist in base that will calculate Euclidean. And we will do this in code, but some of the distances are very similar to Euclidean distances, so that's okay. So that's what I was saying, like because of the abundance data, if you plot the position of the communities along the axis, the fact that there can be lots of abundances will take your points apart and will make Euclidean distance grow further than it should. So you have to normalize to standardize this data before you calculate the distances. And between species and variables, between environmental variables, it's something that is more common in other kinds of analysis, because you can have correlations and associations between variables. So it's not a thing that I will talk a lot about today, but the idea is the same. You have a matrix that has sites, and you have different variables. So you must have heard about principal components analysis, for example. This is the kind of analysis that you do in such a matrix. And we will do principal components analysis, but in this context. One of the things I won't stay a lot here, but one of the mathematical properties of the similarity indexes that made them easier not to plot in a two-dimensional plane is whether they are metric or not. And some of these dissimilarity indexes, like Bray-Curtis, are not metric. And what does it mean to be metric? Is that it looks kind of simple, but you should have between two objects, the distance from A to B should be the same than from B to A. And some of these indices do not have this. And if some two units have the same properties, their distance should be 0. There's not necessarily an upper bound. For example, Euclidean distance does not have an upper bound. It can be infinite. And they should follow the triangle inequality. And that means that their distances should form a 0. You cannot have, if you have a distance from A to B and from B to C, the sum of these should be larger than this. You cannot have a shorter distance, because otherwise B would fit somewhere here, and this does not work as a triangle. This is just something that at the end, when you perform the analysis, that makes that you have to transform, and some analyses are metric and some are non-metric. Okay. So now I will start with clustering. When we talk about multivariate data, we talk a lot about classification and ordination analysis. And classification is what we call cluster, basically. And depending on the language you're using, it's agrupamento or clustering, or I think most of us use the English term. And cluster methods are made to find groups in the data. Spoiler alert, even if they are not supposed to form groups, cluster will form groups, because that's what it does. And I am talking about dissimilarity and similarity because the cluster is formed based on the dissimilarity and the similarity. The in-group similarity should be high. The similarity between groups should be lower. So based on how you measure similarity, you will form your groups. Please. Do you have a mic? I don't have a mask today, sorry.
I don't know the name in English, but the analysis PCA make something kind of similar to clusters, the data.
PCA, Principal Components Analysis. It's the second type of analysis that we're going to talk today. That's an ordination. The cluster creates groups, and the PCA, if you plot the PCA, you can find groups visually, but not necessarily they are. You can plot a cluster on top of a PCA, for example. But the PCA is just organizing your data along axes. So it's not exactly the same. But I will talk about ordination in the next part. So cluster. We will have to talk about the similarity measure and the clustering method. And we have two large types of cluster that are used in ecology, at least. There are lots of others used in other areas, but k-means, you have maybe heard of k-means. K-means, with k-means you enter the data and you tell the data you tell the analysis how many groups do you want. So this is a decision that you have to take. And it's a divisive algorithm. If you have your data, what it will do is that it will, I have the figure for this. It will start dividing the data in the number of groups that you asked, and then it's going to start adjusting the presence or the belonging or not to the groups. But if it's a 2 or a 3 or a 4 group, it's your decision. And this is something that is going to happen a lot. The decision of the person who does the analysis can change the result or not. But it's a divisive algorithm in comparison to hierarchical clustering that is maybe, I don't know if it's more famous. But you don't have a predefined number of groups. The analysis gives you a dendrogram that is joining pairs by pairs the entities and the clusters. And the decision of when you make the cut for a group or not is one of the decisions that you have to make. So k-means cluster functions like this. You try to make within cluster variation as small as possible. So at the beginning, it starts randomly. This is step 1. It will just assign the observations randomly to one of the groups. It will calculate the centroid of the 3 groups this is an example with 3 groups. So for example, in the first step, it assigned randomly to the groups, and in the second, it calculated the centroid for each group. Here. And based on this difference, and the first random step did not do, it was random, so the centroids are quite close. So based on these centroids, it reassigns the closest points to each of the centroids. So everything that is closest to this orange centroid is going to be group 1. Everything that is close to this second centroid is going to be group 2. And it starts again. It recalculates the centroid. Now the centroids are apart because the groups were assigned based on the similarity with this point. And when the new centroids are calculated, you reassign. So some changes will happen here at the borders, but at the end you have a robust, at the end it stops changing. Hi.
One question. You need to define that will be 3 centroids, right?
You say the number. This is an example with 3.
But you need to put this number.
Yes, you have to say.
So, but how you can decide this?
There's a... No, please. I have the other. Yeah.
It's very debated about how many groups are you going to need to take into account, but there are some packages in R that can tell you to define in a non-biased way or less biased way how many groups do you need, but it's according to the data. But at the end, from my point of view, it's kind of arbitrary.
Yeah, it is. It is, and that's a problem, but sometimes it works for what you want. And we are not going to go down the hole of becoming very good at k-means, but if at any time you need to, there's indeed ways to, there are ways to improve every analysis that we're talking about here, but yes. But it's basically you decide, and that's a problem. After that, you go ahead, Andrea.
In this, I don't know if I understand very well, but in this kind of analysis, we kind of make a multivariate analysis, And we can tell one of these variable can be the predictor variable.
This is a two-dimensional representation of a multivariate situation. So these could be environmental variables, for example.
And this one could be the predictor variable, and then others response variable.
No, I would no. It's the response. The responses that belong to a group at the end. Like this is, you do not mix presence absence of absences, and we seldom use k-means with species presence, more with variables like environmental variables. But it does not work in a logic of the response and the predictors. It's like it's there, and you're splitting the data. So it's the object of study is the data itself. You, of course, after you have these groups, you could check the belonging of these groups to other variables. For example, if you have the management practice, then you can check if the groups make sense in real life. Like, oh yes, these 3 groups exist, and when I check at the values, they do form distinct groups. But it does not work as a response and predictor logic. You're splitting your data. Why I am here? I don't know why.
In these cases, like you have, you're trying to categorize because in the response predictor, you would have like a number as a response. But in this case, you're trying to like categorize your data.
Yes, yes, basically.
So, can you give me an example with this species so that I can?
Sure. For example, you have this is like an exploratory thing, so we don't have this logic of having the environmental matrix in response of predictors. This would be modeling, and this would be what Sarah told you, and like the rabbit on the hole was like modeling, and you don't, and in this case you don't have the responses are vectors, they're not matrices. What you're doing here is exploring the matrix itself. So for example, you have pH and temperature and precipitation of a series of sites that can belong to categories, for example, management or kinds of ecosystems. But what you do is you use the continuous numerical data to be split into groups. And then after that, you can check if this fits, because sometimes you don't have this. Sometimes you don't have even like a treatment, or you just want to check the pattern. So for example, I have the Brazilian Atlantic forest. There are some analyses that say that the Brazilian Atlantic forest is divided into 2 latitudinally, and depending on the distance from the sea, because you have more humid areas, and you have drier areas, more seasonal areas, but also there's a cut at one river, and there's a cut that is latitudinal that makes it different. But I don't know I don't have a way to label each one of the observations. If I put a point in the Brazilian Atlantic forest, I can check the vegetation, but sometimes it does not fit, or sometimes you don't have the data. I could take the whole environmental data of the whole of the Brazilian Atlantic forest and ask a k-means to give me 3 groups. And sometimes it's tricky, because it can take the whole Brazilian Atlantic forest and tell me, yes, one of the groups is here, and it's a little desertical place, and the rest of your groups is here. And you, like, if you have two groups, you would expect, like, give me the group in the south and the group in the north. But sometimes, due to the nature of the analysis, it's going to be, yes, your cluster 1 is here, your cluster 2 is here, and the rest of the group is closer. The rest of the points are closer to each other than these 2 outliers. So it depends a lot on what you're trying to do. But what I'm trying to say is that sometimes you don't have the label of the data that you can create a cluster. And in some other areas, sometimes this is a way to create an initial label, like 1, 2, 3. and then we start the analysis with other kinds of data, because you don't have a way to classify them beforehand. Is it okay, Maris? And actually, we are not going to do code with k-means today. We're just going to use the other kind of cluster, but it's definitely there. And sometimes, depending on what you'll do, it makes sense because you don't have the number of groups, but you want some classification into groups without having it. I lost a figure here, but okay. So the other kind of cluster is hierarchical clustering, and instead of starting with 3 groups, for example, belonging to groups of all the data and splitting from the top down, the hierarchical cluster starts with the closest pair of observations. So, for example, if we have the data, I will just make a figure similar to the previous one. Assuming that you have data plotted in a 2-dimensional space, what hierarchical clustering is not going to do is saying, okay, each point goes to a group. What it will do is just define which is the closest pair, and it will say, like, here, this is the closest pair. And this is the closest pair. And I have to check which is the other closest pair now. So maybe it's this one. And at some point, what can happen is that the closest entity is not two pairs of observations, but 2 pairs of groups. If you have 2 close groups, like if I had, for example, here a group, or like, I don't know, things that were joined here, maybe I would decide that these are the 2 closest entities, not points. And the resulting graph here are tree-based graphs. So this is the cluster that you already are familiar with. And this is the ones that we're going to do. So for example, you will have a tree that joins the closest and joins the other closest. But you have another group. And this is the group that is closest to the other group. And you go and start joining the closest pairs together. So at the end, you have a tree-like diagram. That is not what k-means clustering does. K-means clustering just gives the assignations to the groups.
This one, you need to define the until how much groups you want, right? Like, you need to define the limit because then you can join everyone in the group. Now,
in this case,
yeah,
everybody will start like the tree will the dendrogram will definitely have a root. Like everybody is going to be united at some point. It looks like a phylogenetic tree.
So you are not different. So what's the meaning of this? To do what? I didn't get it.
It's to understand the closeness. I will give you an example with vegetation. And vegetation is such messy data that it makes sense because sometimes you want to see what is closer to what. And it is not a geographical proximity. But at the end, this is part of the thing. K means you have to choose how many groups. And with a cluster, with a hierarchical cluster, you do not have groups at the end. Depending on how the cluster likes and looks, and we are going to play with that in R, you can have dendrograms that look like 2 very distinct groups. So at that moment you say, okay, I have 2 groups, and the cut, what you have to do is to choose a cut level. And when you have a cut level, you say like, okay, this is a cut level, I have 2 groups. But this is your decision. The decision of the cut level is yours. After deciding the distance and the clustering algorithm. So it's a series of decisions. And some forms of the dendrograms are very hard to make a cut tree and you say like, hey, I have distinct groups here. So it's another way of thinking about this. And there are different linkage functions, and they work differently. I will just So so in my example, in my ugly example, I can have, for example, here a cluster, and I can have here another cluster. They have been already joined together. And because they were closer to each other when they were points. But now that they're clusters, I can decide, how can I decide what is closer to anything? I will just do this, for example. There's another cluster for any reason in another dimension. The complete linkage function will only link to groups for which all the elements are closest. So for example, all the elements of this group are closest to all the elements. So it will basically take the maximum distance, and it will decide to join it these two rather than this, because this is a distance that is too large. So the complete is like, I will only join whole groups. The single is exactly the opposite. The closest is going to be already the next linkage. So this is a single function. And this single function creates dendrograms that look like this, because it's basically joining one by one sometimes. Because it's too short, it requires only very short distances to join. Average, which is more robust, will take the centroids of the groups and will decide which is closer. And I'm talking about Euclidean distance, that's okay. The average will join the closest centroids together. And word, it's a more robust algorithm that will try to minimize the variance of the groups. So you will have clusters that look very like, they are super tight because they don't vary a lot. So they minimize the variance. You can weight it, and the average and centroid. Sometimes the average is not the centroid. Sometimes the average is not the centroid. You can have a geometrical centroid, and you can have like an average that is slightly displaced. So yeah, it's different things. To take an average and to take a centroid, a geometrical centroid, like. The values, yeah. It will weigh the abundances at the end. The centroid is going to take only the central mass. But I will check about this because, yeah. Sometimes the centroid is not the average. Wait, I will go back literally to this part. And of course, which distance measure? So. We use Euclidean or presence-absence distances.
I have a question. How can we decide which linkage function is better for our case of study?
There are a posteriori ways to see how were the groups, but currently, like I will say something that I shouldn't. It's like you avoid complete and single, because they do create clusters that have very difficulty, and that they don't mean necessarily anything. Like taking the closest all the time is not necessarily what you want from your data. But after you have the group and after you cut, you can check if the variance is good, if the distance between the groups makes sense. Yes, it's more a posteriori thing.
Andrea?
Hey. What? Word?
You said we avoid what when defining the? You were saying that.
What kind of linkage we avoid?
Like average and centroid and word are more robust when you check at the groups. And there's another thing, since you can have different results when you do different clusters. Are those clusters valid in nature? Sometimes when you change from centroid to word, for example, some groups are really robust, they still exist. And you can say like, okay, this is really an entity. But you never stop at, I choose one and I just continue.
About the question between average and centroid, seems like centroid is the centroid, like the mean of the positions, and you take the centroid. And average, you take the distance between each pair, and you take the mean of the distance.
Okay.
Yeah.
That makes sense.
Yeah.
That makes lots of sense. Thank you. But also, yeah, it's centroid is more like a median than an average. And you have weighted options. The average of the like all the segments in the group will have a distance.
So then you have an average distance.
And then the average.
But you're not at a point.
But you're not taking the other ones. Yes. Like the average, if you're going to.
What he say?
Okay. No, I have one all the time.
What's saying here is that average linkage is where the distance between each pair of observation in each cluster are added up and divided by the number of pairs. You take a mean. You mean between the distance between each point of two clusters. Okay? And when you I think that they try to minimize this average linkage. I think.
So if you add a point, it won't add too much to the average. That was Word does with the variance.
Yeah.
We can come back to this. Definitely.
Like the average between clusters, average between small set of points.
The centroid.
Is like the average of some clusters that I already have.
It's the distance. You take the distance between. I think what average may do is like it does not take a centroid, but like it's a point that is in the middle of the cloud that is not exactly a centroid. But at the end, you join two groups when you minimize this distance between the two centroids or averages, depending on. So I was telling you, the cut level creates different numbers of groups, and you only interpret the y-axis. At the end, this cluster is like a mobile. I don't know how to say it in anything. Like a hanging thing. You have hanging branches. Imagine this was a cord, and this was like strings, and these were floating in space. This can rotate. The fact that a branch is closest to another one in the horizontal space does not mean anything. This can vary. This can rotate. So the only thing that we interpret is the distance here. We're not going to use penguins. We're going to use H-clust. And I have this here. Do you want to check this? Do you want me to talk more? I don't want to talk more. Because we could start exploring hierarchical clustering, not k-means, and then I go back to ordination, because it's a slight shift of areas. I will just. We'll just go offline. I will like. So for now, wait, give me water. We're going to use package vegan, and we're going to use the Dune data, and in the repo you can create a new script, and you can load vegan, and you can load data Dune. And data Dune env.env, which is the environmental information. I will just push. Vegan.
No, the other
The package? Cluster. Yes. It's because it's function hclust, but it's cluster. Yes. I don't have the link for the tutorial here. Tutorial. Here. Check more. And when you load the data, the Dune data, here. So I want you to check that the Dune environmental data has a category that is called management. Hi. Yes, I am going there. I just don't want you to. I wanted to push this. I wanted to push it.
Andrea?
Oi.
Sorry, what we have to do?
I am just pushing the tutorial so you don't have to follow only my screen.
Okay.
But for now, you can load vegan and H and cluster and load the Dune and Dune env data and check that the data set Dune has some management categories. So In the help, you have the description of every management categories. And one of the things that we are going to do, the similarity, is calculate two distances between areas regarding how they, how close they are, how shared species work with them.
Is it there?
It should be because I pushed. No. It's because I didn't push hard enough. Não, tá ainda não. Just give it a second to load. The site has to build, so it's a little tiny.
What do you use
To build the site? It's called Distill, but it's based in Markdown. And we're going to talk a little bit about Markdown soon.
Do you know
Excuse me?
Do you know QBio? Is it similar to QBio?
Yes, basically.
The only one I think it's an engine to generate static websites.
So I don't know if you have seen the repo for the site. It has the slides and it has the site itself in code, like in text-based.
Oh,
That's and we have a builder that builds the site alone. So this has been a way to organize things. But I don't know if it built at the end. Ai, amiga. Ah, porque eu não sei fazer links. So it should be in this multivariate analysis one. Of course not. Fue? No. What? Ah, using the link. Como el address, the address. Yeah, sorry. So it's there, but I put a wrong link. Can you copy this address to Slack? So, I need split screens. I am so sorry about the split screen setup. I just hate having one screen only, because I cannot show you things. This is going to stay here? Okay, perfect. While I... Camila. Camila is going to put the link, the correct link in the Slack, if you already found it or not. Okay. What time is it? It's 12:20. So this is not going to take much. I already have said everything, basically. But I want you to see how does the code for a hierarchical cluster works. So of course, read the whole help of VegDist. It has lots of information. It had lots of indices. And I want to point you to Orlowski's coarse distance. Coarse distance is basically a Euclidean distance. If you see the calculation. It's a Euclidean distance, a normal distance, calculated into a normalized matrix. And what it allows you in the future after that is to use PCA, which is not a good analysis for this kind of data. If you have good indices, if you have good distances, then you can use PCA, because it has assumptions of linearity that do not hold, and because chord distance solves the problem of large abundances. At the end, what it does is, imagine it's putting the whole points in a sphere, in an n multi-dimensional sphere. It's putting every one of the sites in the surface of this sphere, and the chord distance is literally the chord. So how close are entities in this sphere? So you don't have Euclidean distances that are very, very large because of the abundances. So it's just a way to make Euclidean distance work for this kind of data, for PCA. So this is why I put in here. Bray and chord are just two very good ways to compare the composition of communities. And I would like you to check. Do I do this?
Andrea, just, I'm sorry, here.
Okay.
What is the Bray-Curtis distances doing? I didn't get it.
The thing, like when we use Euclidean distance in community data, if I have like a space here, the fact that sometimes the species are very abundant takes the points of the entities very far away, because they have lots of dominance. And when it takes them very far away, Euclidean distance is not telling you anything about the proximity of the entities, because they share or not species, but it's only reflecting this abundance, this difference in abundance. So it just does not order the communities, or it just not puts them together according to what they share or not. The normalization takes the data that goes from 0 to the number of individuals per species, and it centers them, put them into a 0-1 interval. So mathematically, it's like if you put everything in a sphere, and the Euclidean distance of entities that are in a sphere is the chord. It's like the chord of a circle. So that's why it's called chord distance.
Just put them for cluster points so you can measure with chord.
It standardizes it at the end. It preserves the relationship between the entities without being affected by these differences in abundances. So the nice part is that you're using Euclidean, because you're not using Bray-Curtis, that is using shared and non-shared species. And with Bray-Curtis, you cannot do a PCA, for example, because Bray-Curtis is what is shared, what is not shared, but it does not have a mathematical representation that you can order after that in a PCA that is linear. But chord distance allows that.
This Dune variable, or it's not a variable, it's I forgot the name.
It's a data frame.
Data frame, yeah. So the column will be the species. Yeah?
The Dune, yes, it's a community matrix, yes.
Okay, and the line will be a place.
Yes.
Okay, but this distance that you are discussing there, what is this? It's like a multi-space with each...
It's between sites.
It's like a 20-dimensional space? Or
It's like a what dimensional space? Like a...
Because you have 20 sites.
Uh-huh.
So, for example, I take the distance between these two first columns.
No, between the two first lines. Between sites. The species are the descriptors of your sites. The species are there. The species are not the ones that are being analyzed at this point. It's each one of the sites in the lines.
Okay.
What you want to do is check which site is more similar to the other, if the dune vegetation follows gradients. So when we are in a dune, it's like you have the sea, you have the forest at the end, you have a gradient of salinity, you have a gradient of temperature, you have bad soil because it's super sandy, but when you go to further from the beach, you start having soil. So you have like environmental gradients that change, and you don't know how vegetation changes according to this environment, for example. And you have some species that only can live in the sandy parts, and you can species that are just like, they don't care, they live wherever. So when you sample sites in this way, you start understanding what is the answer of the species along some of these environmental gradients.
And this distance will be the distance between each species between two sites, and you sum everything?
Yes, yes.
Okay.
So this site is present in some of the and when you go to the dune.end table, you see that the sites have soil pH and management, and sometimes you have like destruction, like disturbances, killing the vegetation, this kind of thing. It's in the help of the Dune dataset. If you want to play with the linkage, I just used the final version. I used average for starters, but you should check how method, like the linkage changes the shape of your cluster and how you use this. And there's a function that is called cut tree. And of course, base R's functions for plotting are horrible, so I just added a little bit of tweaking that should also help you like see how R plots. If you have any questions about how R plots and what I was doing in this kind of code, you can tell me.
I don't know if I got lost in the middle, but why do we have this y-axis height here? It represents something? No.
The height is the distance.
Is the distance?
The height is the distance. It's the representation of the Bray distance and of the core distance.
Okay.
Okay. If you change distances, like they are, I didn't want to make like we have 15 ways of calculating distance, so we will have 15 ways of the cluster. Nobody works like this. It's like you you compare a couple of them, but you.
Okay.
And
but you can measure the
you
distance?
can see also that depending on the distance, the groups are different. You have, for example, you have 14 is similar to 20 and 15.
Yes.
And you see that 15 and 20 are still similar. But 16, which was closest to 15 using Bray,
no, it's here.
it kind of changes. But so, for example, the cluster that is creating 14, 16, 15, and 20 is more robust in itself than the organization inside it. So you say, okay, if you would cut the cluster at some point, you would say, like, this is maybe a cluster. These 4 sites have something in common in terms of their composition. We are just analyzing species composition right now.
Thank you.
The plotting in the tutorial is ugly because of the space, but if you do it locally, you have a way to see the numbers more different. So this is not nice either. Yes. Okay. Yes, you have the counts. Okay. It's similar to Cestus data. It's similar to. I will just perform this. I will just do it in our repo.
Andrea, I have a question.
Of course.
When you did the not so ugly plot, you redimensionalized the y-axis, right, a bit? So the values changed?
What I did was...
Yeah, the values changed in the y-axis,
yes,
right?
it changed. What I did was just, since the important part of the cluster is the hinges, the height of the differences, where the final tips are, it's not important, and I don't like this. This is not an informant. This is too noisy. But the part that has the information is the hinge, like the height of the split. I used hang -1, but it's like anything, any value that is below 0 will put all the tips in the front, in the back. And what I did was, accordingly, I took out the axis and I wrote the axis, because it's still ugly if you don't do this. Please play with it. I would love to. So we have a couple of things going on here in the plot. When I am not going to stay a lot of here because we have half an hour. I will just stop. Okay. In the last, how are you doing about this? This should be like, it's not super. You can play with the linkages. Next time you see a hierarchical cluster, I hope that it's okay for you if you haven't seen this before. I will come back to the. Okay. Just for the sake of time, I will interrupt you because you have the code and there are other things that you can do. And if you have questions about the plotting part, the R part, also just make it. And I will be here at the end of the class. But the other analysis I wanted to speak about today are ordinations. And ordination, in contrast with classifications, cluster is classification analysis. And ordination is trying to summarize the variation in your data sets along axes that represent most of the variance. Okay? So when you hear about PCA, PCA is an ordination technique, and it's not the only ordination technique. And you have, every time you have the samples in a 2-dimensional space or 3-dimensional space plot, it's an ordination. It's, in ecology, we call a gradient analysis. This is like the way it was presented to ecology. It existed outside ecology, of course, but the idea was to check how species and sites are organized along gradients. So this is why we talk about gradient analysis. And we have unconstrained ordination. We have only the ordination of the data itself. And we have constrained ordination, which I think it was Cristiani was asking, or Andrea. Constrained ordination starts with the logic of the predictive and the response variables, because what it does is that you can have an ordination of the community matrix, and you will have axes that summarize the variation in your data. And when you create a constrained ordination, this becomes the answer, and you can use the environmental data set, for example. So dune.env, that is another independent matrix, to tell as an explanation. So you will have something that looks like an ordination, but has some of the variables there. It will just help you understand the relationship between species and variables. Okay? I don't know if you have heard about correspondence analysis, for example, or DCA, the trended correspondence analysis, or PCOA, principal components analysis. Everything is ordination at the end. It just takes different paths and distances and different logics. So the most famous is the principal components analysis, and we are going to use only the environmental data to do this, because it's numerical and it should not have NAs, and it should be, it does not work well. You can use binaries and categorical, but it's not exactly the purpose. And what principal components analysis is, it takes the whole dimensions of your data set. If you have 13 variables, you have 13 dimensions along which sites can be ordered, and it will make a dimensionality reduction. It will try to keep the variation in your data while creating meaningful access that you can interpret easier than the 13 variables. So it creates low dimension representation of the data set by retaining the most amount of variation in the data. It's widely used. And you should have, ideally, numerical data. So binaries will be taken into account as zeros and ones. Categorical should be recoded as ordinal. So it's not exactly the most flexible analysis. Other analyses are more flexible. And you shouldn't have missing data. This is not the kind of ordination that leads well with missing data. Other ordinations lead with missing data. If you have data that are very specifically like lots of missing data, you can check other kinds of analysis. And numerical data should be standardized, centered, and scaled. It will use the covariation between the variables to extract the axis of variation that gather the variation. So what it does is, there are a couple of methods to extract those principal components. But basically, it's examining the covariation, the matrix of covariation. So you will have the variables, and you will have the variables, and you will have covariation. And it will transform the matrix of covariation into a matrix that has everything is 0, and the diagonal is taking the variation. This is basically a matrix operation. And each one of the principal components is the axis, and the weights of the principal components will tell you how much of the variation, the original variation in the data, is from the original data is in each axis. And it will decrease. The first axis will summarize most of the variation in your data. The second will summarize less variation. And the fact that this operation is performed makes the principal components orthogonal. So it's independent variation. All the PCs between themselves are orthogonal. They don't covary between themselves. In R, you can have print comp. There are lots of ways. And in ecology applications, and today in vegan, we're going to use RDA. RDA stands for Redundancy Analysis. And redundancy analysis is the constrained version of the PCA. So it's the same, it uses the same function. And if you come from other areas, of you are using other kinds of sources, when we talk about ordination and about clustering, these are methods of unsupervised learning. You don't have pre-labeled data. This is unsupervised, you're just extracting variation from the data. And how many principal components you will extract, it depends on the number on the importance of each one. I think it's better to do this in the code. And the other ordinations techniques that are important in ecology are the correspondence analysis, which is based on chi-square distances, because it's based in chi-square, so it's presence and absence. So it will be able to take co-occurrences into account instead of linear relationships. The principal components analysis, principal coordinates analysis, there's a typo there. It uses any distance matrix. So for example, if you have Bray-Curtis, which is not good for PCA, you use a principal coordinates analysis. It will ordinate this data. It will be able to ordinate this. And you have also non-metric multidimensional scaling. It will just represent the distances without taking into account, without being too strict about the reality, it will just represent, it will make the best graphical representation possible, and it will iterate around it will iterate a little bit to reduce the stress of the distances between the distance matrix and the dots. When you talk about molecular data, for example, there are like TSNs and other ordination data that are also iterative. They will just check if the clouds of dots are representing reality. And I was telling you about the canonical versions, canonical and redundancy analysis versions, which is when you use a second matrix. And for this, I don't want this. We will still use the Dune-Env variation, the Dune-Env data set. So some of you have asked me about the repo. How are your repos? More or less. I have seen that some of you are putting the tutorials, and I know that what has happened these 2 weeks is that I'm starting a topic and it ends in an explosion of possibilities. So we don't have like a final version of like, yes, this is the final of the analysis. But the idea is for you to have an idea of which are the rabbit holes in which you, according to what you want, according to what you need, can enter. But still, one of the aims of this module is to be able to organize some data. So I myself have lots of trouble organizing myself while I code. You have seen me code. I'm just like, brah, 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 brah. And then I have to stop and check like, no. What I did was horrible. I have to comment, so I come back, I comment. I do my commits. Like the moment where I put my head together a little bit is the commit. So what I saw yesterday before, we were doing a function and it changed, so I came back and at the end, what I checked is like, it is running, I am commenting, I am doing the commit, and this is good enough for me to come back later and say like, okay, I can continue. So it's a way to be good collaborating with yourself even. So yesterday, for example, I was trying to organize the data while we run this for, and we created the function. So I tried to explain why we did some things. Okay, and this is a way, like the commit is the way to organize. So please do. We are not having tutorials with a start, middle point, and end. We are just like, but the commit is still a unit that we expect, like until what point? And because you have the helps, you have your own interests, so you can just continue. But please try to make them like organized as possible. Like everyone has different ways of working. I cannot create a first code that is clean. Like I am just like a mess. But this is a way that I have been using to. And so we're going to create I guess today you already created a new script. Okay. So I won't start with I won't show you the tutorial, the part with the cluster. Wait, no. I don't have, this is not good because I don't have the whole, okay. I want to know if you have any questions. Had you already saw these kind of things? I see people saying like, yes. Have you executed it? Had you executed in R? Okay. Plotting and doing the analysis, that's cool. Yeah. In which kind of data? Actually, it was also on Dune. Okay. Okay, okay, just like the tutorial way of doing. Okay, okay. When I had to learn about this using forest data of in places that burned. So I had groups, I had places that burned more or less. But I didn't know what were the extension of the changes when things burn or not. And I had soil. So it was like crossing matrices. It was part of the tutorial. I have. So I will just create my script for today. And basically what I'm going to do is show you how you do an ordination in vegan. I will put this same code in the end. And this is mostly taking like the documentation of vegan. I haven't talked about vegan. Like vegan is created by the numerical ecologists of the world. Like it's an international group. The leader is in Denmark, if I'm not mistaken, but it has like some of the people who create the analysis themselves. They put it into vegan. So vegan is huge now. It has been in circulation like for 15 years or more. And the documentation created by the people are just very, very good. So I will just load vegan and load Dune and load Dunen. And this is something that you already did. Okay. Sorry. And we have a core distance. We had a core distance version, which was the Euclidean distance of the Dune data. And I didn't show you this function, the decostand. The decostand is one of the functions that show you how to standardize data. So what we are going to do is decostand the matrix of community, decostand, Dune, and normalize it so it gets the core distance. Core distance. So if you ask any core distance, any distance matrix, it's a dist class. Okay. And since this is core distance, I was telling you that PCA works with core distance, which is not exactly the same. If we were using Bray, which is not a metric analysis, we would have to use PCOA. But since we're using chord, that is an Euclidean distance, we're going to use PCA. And I was telling you that RDA is the way to do PCAs in vegan. There are other ways to do it. So basically, we are using RDA function. And I will just always have the help open. And the help is cool because it returns you the help of another function. Actually, it just returns you the help for CCA, which is another analysis. But sometimes in R you have this. You have very close analysis that do not deserve having different helps. So you have the whole documentation inside the same because it's redundant. It would be redundant to create different files. So it's a way to organize. But still, in the help, you have RDA as an option of analysis that can be made. And the simplest, so we are not going to use the core distance because PCA does not accept distances. What it does accept is normalized data. So it will take only the decostand part. Decostand. I will just create this normalized. And we will make an ordination. I will create PCA and RDA of the norm. And this should work. And I have no idea why it stopped. I know, it's okay. No, I thought I was waiting for the prompt, but the problem is that this projector is not showing me the prompt, so I was just waiting. But no, it's okay, it's here. Can we change the projector size here?
The projector size?
Like, oh, you cannot. You have to, okay, sorry for the volume. You have to check this other, I don't like a lot the setup of having. So, yeah. So ignore this, and so I created the PCA. You can plot it, and you will see that, as usual, Bézard plots things horribly. But what did it do? The PCA will return the location along the principal components of the sites and of the species. It will let you know where, and you could start, like what people do is starting seeing groups, seeing similarities between sites. So if you remember one of the clusters you made, we had a real cluster between sites 20, 15, 14, and 16. Do you remember it from the cluster? So they do group themselves, or they do tend to the same places along the principal axis, the principal component first. And what you do is you have to have more information about the PCA, but you start watching the patterns. And if you want a summary, it will tell you the position of the sites and of the species. And it will tell you, it will give you the importance of each component. It will tell you something that happens a lot in this analysis, that the first principal component explains 30% of the original variation, and that the second explains 20% of the original variation. And sometimes you will only get to a reasonable amount of original variation after some number of PCs. So the sixth principal component, if you sum them, you have 80% of the variation in the sixth first principal component. Okay, so you will never look only at the first two components. Okay, so you could plot the second and the third principal components together. I will just go back to the help, just to have it while we talk. But you use choices. Plot RDA. Plot RDA is a function. Choices 2 and 3. So I'm plotting the second and the third principal components. So this is now the second component that had 20% of the variation, and this is the third that was going towards the screen in the last plot. And you can see that other patterns emerge and other familiarities. The question is, which environmental variables are varying along this axis? Like, this is only the composition for now, okay? You could do a PCA for the environmental, just to understand what happens. Let's do a PCA of the environmental matrix. So, okay, it does not allow me because it has this. fazendo calor demais. So in the environmental data, you have some categorical variables that are not, you cannot ordain them. If hay pasture one is worse than the other, you would have to have information biological. So I will take this from the PCA of the environment, and we are just going to use aluminum moisture and manure to make a simple PCA.
Professor?
Of
Why
course.
The PCA stopped in the 19 principal components?
What does it have? 19?
Yeah.
20? Because the set has 20
Yes.
sites.
But it stopped in 19. I don't know why.
Where did it stop?
When you make the summary of PCA,
so we have 30 species and 20 sites.
yeah.
And what you say is that the PCA is
Yeah, run the summary. Try to run the summary.
only 20 principal components?
No, 19. Yeah. If you go up. Yeah, it is one. 19.
You know, I don't know. Like, I would expect the same amount of species of environment as.
Yeah.
I have never seen this, but I don't see the 20. Yes, 20.
Actually, there are 30 species, right? 30 species in
30
20.
species.
Yeah. So I was expecting have 30.
Oh no! In this moment you're working in the sites.
Oh, okay.
Okay.
Okay. So, but should be 20 then.
It was a summary. It was a simple summary. Here, it's better. You can see it better here. I have. Of course. What I did was basically an RDA, which is a PCA of the transformed data. So we standardize community data with function deconstant RDA is. Oi.
Is this last PCA run? Because here I'm trying to use one.
Yeah, I think
It didn't love it. Ah, because I put. I don't even have. I think I made a mistake with the number of the manure. AL?
Not AL.
No, but it doesn't go A1. Yeah, that was me. That's numeric.
Because the manure are modes of manure, is that?
Manure and moisture are
Cool. It's because everything is character. Yeah. I would rather use dplyr to change this. So I will select the variables. As numeric. Oh, come on. So what we're doing here. So, okay, I was thinking it was aluminum in the soil, but it's the thickness of the soil layer. What I did was just transforming into numeric in the data. And a plot of this shows you that site 15, for example, has a thicker soil, and 14, and thicker soil and moisture are probably correlated with themselves. I think we could do pairs analysis, a pairs plot of, there are two little points to check which is the correlation. But the correlation will show you that. The correlation between the thickness of the soil and the moisture of it is 0.47. So in the two first axes, they look more correlated, but there must be another dimension where they are just not that correlated. Okay, so when we talk about canonical analysis, it's using these environmental variables inside an ordination of community composition. So this would be like, instead of having two separate ordinations, you have only a sole analysis where you can see everything, like what does the environmental, how it varies, and how it affects community composition. So this is what we talk when we talk about canonical, and this is what redundancy data analysis would do. You can?
I have a question. The PCA utilizes the Euclidean distance to make the covariance pairwise analysis. It's possible to use a different pairwise distance method to make the PCA, because sometimes the data are described by abundance.
A different method for doing a PCA with data that are described by abundance?
Yeah. Use another method to calculate the distance covariance.
There's another method that is called SVN, but it will not solve the fact that you have abundances. Like the PCAs can be calculated, but they will work the same. And if you put abundance data, it will interpret it as it would interpret an environmental variable, like high numbers, high levels. It will interpret it like linearly. And sometimes these species are not linear with this kind of. So what you have to do is transform your community matrix in order to use a PCA. Or you use your community matrix with abundances, because it has, the core distance still has abundances. The normalized version still has abundances. But you could do another kind of ordination that leads with this. But they have not necessarily problems. We are going to do the canonical version. Part of my heart would like to show you how to plot this in a most beautiful way. But the tutorial of the package has it. So it's a very good way of practicing your base plot skills, because you would have to plot everything like I did a couple of days ago. Like, you plot without anything, you add the points, you add the text, you decide the symbols, you decide the colors. But it would be a happy place, but no, not necessarily. So we are going to do a canonical version of this. So it's, hi. It's one. I'm so sorry. We're not going to do canonical. Thank you for stopping me. I will just push this, and I will leave you the link to the tutorial. Thank you so much. And we are going to, we're going to talk next week. I have some references to give you, the packages, and please just chat with me. That's okay. Do you have any questions? Are going to be? I don't know where our evaluation is, if it's the last day of classes or after that. I won't even be here, probably, because I don't. So somebody's going to make the evaluation for you. The 15th? Okay, I won't be here. I won't be here, but yes. So Sarah and I will just send you the evaluations and the rules. We will. And see you next week. Thank you for your patience.
repositório da Sara e eu não consegui achar os arquivos.
Por quê?